So yesterday in class you learned about the first part of the fundamental theorem of calculus, and it's a really big deal. It shows that these two huge ideas that we've been studying, the area between the curve and the x-axis, and also the slope of a curve, are not only related to each other, but they're inverses of each other. And so the only thing that's a bigger deal than part 1 of the fundamental theorem of calculus is part 2 of the fundamental theorem of calculus, and that's what we're doing today. So just a reminder that part 1 of the fundamental theorem of calculus said that if you take the derivative of this new kind of function that we talked about, which is a definite integral function, if we take the derivative of that, we wind up back where we started, basically. So the derivative and the integral kind of undo each other, and you wind up back at f of x. That's saying the rate of change of this kind of accumulator function is equal to the accumulating the area under the curve function is equal to the curve itself. And part 2 is actually even more powerful because it gives us a tool for evaluating integrals. So far we've used area under a curve to evaluate integrals, and we've used LRAM and MRAM and RRAM to estimate how big an integral is, and we've used those integral properties to evaluate integrals. But now this fundamental theorem part 2 gives us another tool. What it says is if we need to evaluate a definite integral from a to b of some function, then all we have to do is figure out any antiderivative of this function. And by antiderivative, I mean figure out a function that if you take the derivative of it, you get f. You get that function. So if you take the derivative of big F, you should get small f. Oops, not f prime, but just small f. So big F is an antiderivative because if you take the derivative of it, you get that function. And so this new tool allows us to evaluate the area under the curve using antiderivatives to do it. And it goes back to that idea that area under the curve and derivatives are somehow related, and that's the fundamental relationship that we're looking at in calculus. There is a proof. We're going to skip it for the purpose of this video. If I were here today, we would talk through this proof, but if you are curious, it's also printed in your textbook, and we'll talk about it when I return. But we're going to do some examples. So here's a function. There's a graph of the function as well. And we're trying to find what is the area between -1 and +3 under this curve. And according to this new fundamental theorem of calculus part 2, all I need to do is figure out something that gives me this as a derivative. So if I go backwards, remember the power rule, we would subtract 1 from the exponent. So this negative x cubed is actually going to be negative x to the 4th. But if I take a derivative of negative x to the 4th, I would get negative 4x cubed. So in order to get rid of that 4, I'm going to divide by 4. Okay, convince yourself that if you take the derivative of this, you get negative x cubed. And then we're going to find a function that gives you the derivative of 3x squared. Well, that would just be x cubed, because you bring down the 3 and you subtract 1, and you get 3x squared. And then we need a function that gives us the derivative of 1, and that would be x. Now we're going to plug in the limits of integration. So this is how we use this second part of the fundamental theorem of calculus. First step is we find the antiderivative. So the second step is we're going to find, I'm going to call that antiderivative big F. We're going to do f of 3 minus f of -1. So I'm going to plug 3 into this function. So I get negative 3 to the 4th would be 81 over 4 plus 27 plus 3. And now I'm going to subtract that. I'm going to subtract, and I'm going to plug negative 1 into this function. So I have negative 1/4, and then negative 1, and then negative 1. Okay, so I have negative 81/4 minus negative 1/4. So I have negative 80/4. And then I have 30. And then I have minus negative 2, so I have 32. And then negative 80 divided by 4 would be negative 20. So 12. So it doesn't really look like it, but this area is a nice whole number of 12. We used this new technique of doing an antiderivative because this particular shape doesn't have a nice area formula. So now you're seeing that we can use integrals and this new antiderivative technique to find the area of new shapes that we've never been able to find the area of before. All right, we're going to do this one. So we have 4x to the 1/3. So we need to first find f, find the antiderivative. So something that gives us 4x to the 1/3 as a derivative. So that's going to be, let's see, we would add 1 to the exponent. So it would be x to the 4/3 would be our new exponent. But if I took a derivative of this, I would get 4/3 times x to the 1/3, but I don't have 4/3, I have 4. So it must have been 3 times that. Okay, so test that out. If you take the derivative now, if you bring this down, you have 4/3 times 3, which would be 4, times x to the 1/3. And then we're going to evaluate that at negative 3 and 0. So step 2, we're going to find f of 0 minus f of negative 3. So we plug in 0, and we have 0 minus 3 times negative 3 to the 4/3. And that's not really a nice answer. So this, first of all, this is 3 to the 1, so oops. So we can add exponents and make it a little bit prettier, but it doesn't really become all that pretty. So we have negative 3 to the 7/3. And that's it. Or you could write that as negative 3 to the 7/3. No, actually it would be a negative times a negative would be, 4/3 is positive. Never mind. Okay. So this is another example of one. So we want to find what gives us this for a derivative. So this is the point when those of you who did a great job of memorizing derivatives are going to have an easier time figuring out what the antiderivative is, because you're just thinking backwards of those things that you memorized. The thing that gives us this for a derivative would be sine inverse of x. So that's our g of x function. And we're going to evaluate that at 1 and root 2 over 2. So we're doing sine inverse of 1 minus sine inverse of root 2 over 2. So remember, sine inverse means what's the angle that gives us a sine of 1. So the angle for that would be pi over 2. And then what's the angle that gives us square root of 2 over 2 would be pi over 4. So pi over 2 minus pi over 4, so the answer would be pi over 4. Here's another one where if you did a great job of memorizing derivatives, then this shouldn't be too hard. What gives us this for a derivative? We're thinking backwards. The thing that gives us secant tangent for a derivative is secant of x. So that's our big F. And then we're going to evaluate that at pi over 4 and 0. So secant of pi over 4 minus secant of 0. Pi over 4, the cosine of pi over 4 would be root 2 over 2, so secant would be root 2. And then cosine of 0 would be 1, so we've got root 2 minus 1 for that example. All right. Our last example is something that gives us a derivative of 1 over x. If you did a great job of memorizing your derivatives, you know that the derivative of natural log of x is 1 over x. You're going to evaluate that at e and 1. So we have natural log of e minus natural log of 1. So natural log of e is what's the exponent of e that gives me e? So that would be 1. Minus, what's the exponent of e that gives me 1? Would be 0. So this would be 1. Okay. So what we learned today was a brand new tool, a way of evaluating these integrals that involves figuring out the antiderivative, or what gave us this as a derivative, and then evaluating our antiderivative at the two endpoints and subtracting. We still sometimes have to use area, just as we did, especially with semicircles, we definitely have to use area. We still sometimes have to know our integral properties, and we definitely have to know how to do integrals on our calculators, because there are times when that's our only option. But this is going to be our most powerful tool for evaluating integrals.